All right, let's go with that. I'll correct the stream later on. I'm just gonna check if my connection is okay before we go. All right, let's see what this does. Hey. And my voice is okay? It's perfect. All right, what's up? Hello. We're going to go for a new presentation this time, talking about caching. This is the only time you're going to see me now, because I will disappear behind this camera. I'm going to tell you that this is going to be approximately 2 hours, maybe 2 hours and a half long, so it's going to be a pretty long video. I hope you guys enjoy yourselves and you got comments and stuff. I'm going to repeat myself if I just say that, so enjoy and thank you for being here. This talk was intended for actually the Symfony World this summer, but I was late for my talk, so I didn't have the time to go for the request for papers, so I don't know if it's going to be good or not. Maybe I'll see that later on. All right, without further ado, let's go with that. I could appear on the side here, but I'm still never far away, okay? So let's go with that. All right, I'm going to get closer to the microphone. Hello. Like I said, it's going to be a pretty long talk and intense presentation on how cache mechanics can work and help in a web information system. This talk was intended to make a little journey around anything that uses a cache mechanic actually while working on web architectures, and also was intended to demystify them a little, I hope. Also, this talk will have the mandatory puns across slides, so if you can spot them, I already like you. Yeah, this is probably the longest version I can make of this talk because I'm going to detail everything, and I might upload a shorter version, 1 hour long, in French and English of this. So you've been warned. Please just sit back and relax and enjoy whatever you want it to be. And hello guys in the chat, because I'm also doing this on Twitch live while recording. I will just edit the video later on for YouTube. So, right, if you think like this is for you and this is an important talk about caching and web, you know what to do. And if you think like it's gone, just close the video and have a good day, live your life, whatever you want it to be. But first, a few words about me, just in case you might wonder. My name is William Pinault. I'm what I call myself a ninja because I don't know what to do. You know, I'm just how to name myself. I'm a web architect, a lead developer, an agile coach, a process and DevOps guy. I'm a software craftsman. I'm a cookie enthusiast. I got 13 years of experience in computer science, development, architectures, mostly with web. And I'm currently working in a software company called Neosoft in Limoges, in France, in the middle of France. If you pin something like in the middle of France, you'll probably end up next to me. And also slightly contributed to some open source project like PHP CS Fixer, the Symfony documentation, Drupal, PHP documentation, Composer, PHP framework interoperability group, the PHP thing, it's hard to pronounce for me, and the Mozilla Developer Network, etc. I'm currently a tech expert, a technical project manager, a solutions architect, and a developer, so I sometimes do stuff that I share or fix. You'll find me on GitHub, GitLab, and Twitter. Wait, I'm gonna shut this down. Yep. And I'm also an amateur photographer and a musician, so you can find me on Instagram, YouTube, Flickr, 500px, SoundCloud, etc. Actually, I did the first photo shooting with a model, she's a friend, this weekend. The first photo shoot I did for 20 months, because this is during the COVID-19 situation, of course. And yeah, feels good. I'm on SoundCloud too, and totally off topic, I'm also a pretty serious gamer, so I play Magic Arena and Magic in general, and Apex Legends at the moment, so many other games too, which is why you'll find me on Twitch here, on Facebook sometimes, and Snapchat if those are your things. So we're here to review and talk about the ways computer-based architectures can use caching to serve apps faster and better. Also, we'll be talking and illustrating this talk with a lot of PHP, because PHP represents about 80%, I'm gonna close this call, sorry bro, of apps online, followed by ASP.NET, Ruby, and Scala. So yeah, your JavaScript hype only accounts for 1% after more than 10 years. So sorry Google, you're not here yet. But first, let's watch a short movie clip. This is a YouTube video. I hope it plays well on the presentation. Well, let's go with that. Yep.
Imagine for a minute that this piece of paper,
excuse me, that's Vanessa and that's mine.
attractive piece of paper represents space-time, and you want to get from point A here to point B there. Now, what's the shortest distance between 2 points?
A straight line.
Wrong. Shortest distance between 2 points is 0, and that's what the gateway does. It folds space so that point A and point B coexist in the same space and time. And the spacecraft passes through the gateway, space returns to normal. It's called a gravity drive.
Yeah, it's called a gravity drive. This is an excerpt from the movie Event Horizon, dated 1997. It's actually, I can't believe it's that old. It's actually one of the only excerpts I can show, apart from the unwanted copyright infringement, of course, but this is just a fair use. For this is a really weird horror movie based on science fiction. Like, it's really super weird. So here at the beginning, Sam Neill is explaining how the ship he built uses a wormhole to warp through space. Let me pass the video because, oops, I just did it. So theoretically, what we usually call wormholes, or more conventionally Einstein-Rosen bridges, named after Nathan Rosen and Albert Einstein, are supposed to be structures that links space and time. Though we never saw one of these, they are in theory possible and could be a way to bend space and or time so that people could travel through both of them. Meaning, you could arrive at a point where you make calculations on an information systems and provide it work on it, but you already got the results. The wormholes were first theorized in 1916, while reviewing another physicist solutions to the equation in Albert Einstein theory of general relativity. A physicist named Ludwig Flamm realized there was another solution that was possible. So he described the white hole, a theoretical time opposite of a black hole, and imagined that both black and white holes could be connected by a space-time conduit. In 1935, Einstein and Rosen used the theory of general relativity to elaborate on the idea, proposing the existence of bridges, put the air quotes here, through space and time. So the primordial universe wormholes are thought to have existed on quantic size levels, which is probably approximated 10 power minus 33 centimeters, which is really small. However, as the universe is expanding, it is possible in theory that some may have been stretched to larger sizes. This would also mean it would be time saving, if you wanted to go to the same place twice, you would just already be there. You would already be at another time in another space where you maybe already did, just like something you already did. Of course, this is purely speculative and goes way beyond what we're here to talk about today. So yeah, I forgot. Yeah, caching. We're here to talk about caching. Well, caching is the poor man's Einstein-Rosen bridge in a way, which is not doing the whole trip by already using the same previous destination, just like Sam Neill does with the pen through the piece of paper. Kind of. Okay, that was just an image. What's a cache? Well, there are two things I hate in life, doing the same thing twice, and walking on a wet bathroom floor after putting my socks on. And also, I hate doing the same thing twice. Caching is an architectural pattern based on observation on how software works. It is very effective and works a lot. It goes on all levels of computing, from atomic CPU level to whole requests, responses over internet, and not only the web. So what are the special considerations about caching on the web? Well, there are two things one should consider. The first one is the OZ model, the layer 4 and plus exchanges like TCP, UDP, HTTP especially. And the second one is in the batch hidden backend processing down, which result from those exchanges. So for this talk, I'm going to show you the principles of the most common caching system and how they work and how to set them up. All right, let's go. So first, why do we cache things? First of all, we cache things when they get slow. If we don't perceive slowness, we don't try to fix what is not broken, which is both a good developer advice and a horrible motto in science. I won't spend too much time on what we define as slow, but I can tell you should definitely watch Google developers' presentation on the Rail model, R-I-I-L. Those works which kind of introduce the principles of Google AMP. So we do that when we have repeated application behavior, identical inputs going through a costly calculation process. But also we do that because we are build, with because of CPU, RAM, DB, input, output, etc. Usage in general. So we have non-zero replication costs when things scale up. And also remember about global warming, whatever consumes less saves more. So yeah, let's just cache for that reason only. The digital world is going to take more and more responsibility in that global warming situation. So yeah, caching helps serving any of our requests faster by not using resources for redundant, useless reasons. You can also serve cached response over a down network, servers, etc. We'll see about that in the end. And finally, a non-absolute reason why we would cache is that we can accept a somehow degraded or non-perfect result. Pretty much the same as we don't require machine learning to yet give perfect answer on most models. Pretty much the same as we can accept some slightly degraded browser experience on some less used older browsers for return on investment concern. We can accept sometimes that getting an outdated, somehow stale output information is okay, or in a way, relevant enough. And that flow is typically what caching is about: creating, storing a previous calculation, operation, request, and serve it instead of going through the whole process again, which only works if the caching system is faster and requires less resources than the calculation is pretending to cache. Of course, if the cache is slower or consumes more resources, then there's no way to cache, okay? So we just get this generic scheme here. So is it in cache and is it fresh? All right, is it in cache? Do we have it? Is it fresh? So then we just serve the request, the cache previous request as a response that we just get from the cache. And otherwise, if we miss, if the cache is not fresh or not in cache, we just fetch the response and the request. So if we get the response and we cache the response and we return it. Supposing, again, that storing and reading, the efforts for doing that are costing less than the fetching cost, okay? And also one more thing I already mentioned, we're not living the world of simple and non-numerous things. What I usually call the now era of, open the quotes, your mom is 24/7 on YouTube with a smartphone, which essentially sums up what changed in this world over the last 15 years, For that reason, we now manipulate larger datasets, immense data storage quantities, and we have to use continuous data processing to go through it. This is why we also use machine learning and talk about big data, because defining models and searching data can now be outrageously slow, if not impossible. So it's not only about costs. Sometimes it can be literally about the sole possibility of getting a response. And for that, using cache and results cache can be critical and not only convenient. All right, so that was for caching. And what's up with the web now? Because this conversation is just about web and caching. What would be our considerations here? So first of all, we're going to talk a little about how the web works. Remember, web is just a sub-part of internet use. So hello. We'll use this as an atomic architecture element. This is a machine. Can be a piece of software, a virtual machine, a process in a container, a physical machine, whatever you want it to be. And then we're going to need something to link those machines, those devices. For that, we got several pieces of stuff we can use. You already know about networks. We have at disposal network layers, 7 in the standard OC model, different protocols inside each layer, sockets, the channel numbers inside the protocol, files, simple files or pipes, Unix signals, RPCs, shared memories, and a few more variants. And also message queuing if you need that thing. So when you design any web app, you have to go that way. Whatever technology you're using, you rely on that principle. You just do this. Whatever you're doing, even if you're a React or Redux enthusiast, a Python slivering, playing like an Unchained Django, that person building a Flutter app that actually makes HTTP calls, whatever. It actually never changed, even though I doubt people are using Gopher or manual telnet queries on the server anymore. But we still have that C URL, right? That curl thing, yeah, we just still have this. Right, so this is the action we'll be focusing on today when it comes to caching. We just provide a request and we expect a response. But that is why and how HTTP is built. And this is the action we'll just focus on today when it comes to caching. I'll try to limit the domain of this conference to that action. So actually, we just get that. We just put a whole HTTP request here, what you got on the top page. This is actually one that was generated by my browser a few weeks ago when I was doing this talk. And this is the response. So you see, we just got the instruction, URL, and the protocol you're using, which it was HTTP 2 at the time. And a few more, headers, things that your browser sends in. Key value, key value, key value, key value. And you got key value responses plus the response itself, okay? That's just basically what this is about. So let's rock. We see what we can do with that action. So let's see how we combine those elements. I'll try to group the caches, types, and paradigms by category breakdown. This might not be super accurate all the time, okay? You will just forgive me for that. So first, before we venture into the deep defined world of networks, services, infrastructures, etc., we need to remind that there's also, we're still working on the same computer principles. Yeah, computers, those things we have around us, you remember? Because since 1945, the computer architecture's principles hasn't changed that much since John Foy Neumann designed it. Despite little stuff like, the Harvard architecture, burst streamlining, and many improvements, it's close to the same. We got a processing unit here that contains an arithmetic logic and processor registers, and you got a control unit that contains an instruction register and a program counter, this thing here, and you got memory that stores data and instructions, and you got then whatever you want it to be, input and output mechanics, external mass storage. So in the end, we still have CPUs executing code, using RAM to store the results while the stuff is on, and using mass storage when the stuff is off. That's just the same thing. So before you go and install any software, before you execute any piece of code, you have to remember that there's some huge science under the hood. The first one you need to know about is the CPU cache. This is the fastest cache you'll use in your apps, except that you'll probably not use this consciously, just like breathing, This cache is a buffer between RAM and CPU. Its job is to gather and retain the most frequently requested and required data from the CPU arithmetic part so that it doesn't have to use RAM or access RAM, nor to recompute calculations. The CPU caching was invented to solve a growing problem. In the early times of computing, memory was extremely slow and expensive. And so were CPUs. During the 1980s, and more in 1990s, the gap between both processing bandwidths, CPU and RAM, became larger and larger. The clock speed began to skyrocket, but memory access times improved way slower. So as everything went on, and it's getting worse nowadays actually, there was room and a need for a faster type of closed memory. Also, many parts of your operating systems will use RAM as a higher level application cache. All component, abstraction layers, drivers, shared objects, and libraries will do so. When you boot your operating system, you just basically have this started and it already takes some memory. So RAM is still the fastest dynamic external source of information that your CPU can get, the random access memory. But it's mostly made of copper. It has a three-dimensional spatial access structure, and therefore it is very costly and volatile. You know it's volatile. You know those magic numbers like core frequency multiplier, the RAS, the row access throughout, the column access throughout, the CAS, and all those things you set up in your motherboard. You know that weird XMP auto configuration and stuff. Okay, so that is what RAM is about. So about the CPU, that little shiny brick that will most likely turn into an ashtray if you forget to put some coolers on it. The CPU. It's essentially made of what we call levels. Put some air quotes of caching. CPU caches are super small pools of memory that store information that the CPU is most likely to need next. It's closer, the closer the level is to the arithmetic processing unit, the faster they are, the more expensive they get, and the smaller they are. First one usually refers as registers. Those are super small and lightning fast, but are sometimes called the level 0 cache. The level 0 is called level 1 when, depending on CPU and supporting motherboard architecture, is further than that. It's usually storing micro operations only, so most modern CPU, hello, NVIDIA, AMD, Intel, Qualcomm, they easily reach 90-95% hit rates, so those are super efficient. Whatever those caches are, they are super efficient. The CPU cache level 1 is usually inside the CPU itself, and the level 2 and 3 are usually on the chip, and level 4 doesn't exist on every CPU. The CPU cache level 1 and 2 are usually inside each core, if you got a multi-core CPU, which is not the basics for everyone, even on smartphones. The CPU level 3 are more usually shared between cores. You know, this is shared between cores. And of course, the source of that schema comes from Intel, which changes from depending on which CPU you're looking at. So that means whatever you'll do, you will use multiple caches all the time. And don't forget that the RAM, when it's too small, which is all the time actually, or when we deal with more massive cache, we have to fall back to mass storage. It is very similar to RAM storage when viewed from an algorithmic perspective. You basically store values defined with types and you retrieve or erase them, but also on mass storage you don't lose them when you turn your computer off, which can also become interesting in some specific cases. So this happens with general RAM limit extension and is called swapping, just trading one for another, trading the RAM for the hard disk storage, the whatever you want it to be. You remember the swapping, those weird swap file, swap on things with Linux, that virtual memory that can cram your mass storage under Windows on C drive and /private/var/VM on macOS, don't you? Or it could be used also for like intense processing, like games rendering. For instance, if you use Blender, the Unreal Engine, Cinema 4D, Unity, whatever, or video rendering like Adobe Premiere, Resolve, After Effects, etc. Those are mass storage caches, abusively named disk caches. Because I say abusively because if your NVMe looks like a disk, you should probably go to the ophthalmologist. And of course, your operating system uses this a lot. Your RAM keeps recent information like the ls call on Unix, you know, just to see what's inside a comment, you know, in a directory, or your your visual file system explorer with graphics interfaces. You know what I'm talking about, macOS, right? That damn .ds_store plague, like the old spam.db used to be. But this is still limited. So that being said, those caches concern any single application running on any computer. They are involved, but not specific. So let's just go a little deeper with the lower application level caches. Okay, so with the with the higher application caches, that is done with the level ones. Okay, so starting now, we're positioning ourselves at the application level. So the core technologies we use become a choice, and we can configure them. Also, I'm going to show you a lot of application configuration, so please remember those are cherry-picked from different sources. Depending on your chosen version, this configuration could vary, if not totally change, or be irrelevant. One interesting cache is the intermediary code caching by languages runtime. So, for example, the JVM bytecode cache, the code cache, the Python bytecode cache, the .pyc files, if you know what I see. The PHP OPCache, also that was used to be in PCL from PHP 5.2 to 5.4, and then it became native in PHP 5.5 and got its just-in-time integration since PHP 8. Okay, so this intermediary code caching exists in actually lots and lots of languages. For example, this is how the Zen virtual machine defines an OP line in PHP 8.2, the future of PHP, because at this time we still have PHP 8.0 when I'm doing this talk. This is an OPCode. An OPCode determines the instruction type, 2 input operands, and 1 output operand results, okay? And not all of these properties are used depending on the information systems, the information given, okay? So this is just how the PHP engine defines OPCode, okay? If you just go to Python, you'll see the same thing. This is the C Python implementation of this module, the bytecode disassembler and reader for generated bytecode in Python. It's not the same, but it's going the same direction. You see, if you read this, you got the source on GitHub. You can just see you got the operand name, the operand code, etc. So you've got pretty much the same mechanic here. And same goes for the Java virtual machine. It's a stack-based machine where each thread has a JVM stack which stores what's called frames. And a frame is created each time a method is invoked and consists of an operand stack, an array of logical variables, and a reference to the runtime constant pool of the class of the current method. This is part of IBM, by the way. So if you see, it's just the same thing. You got the stack of operators and operands, and you've got pretty much the OPCode of JVM. What JavaScript? JavaScript is pretty much the same, except there are several JS engines. The most common you can see are V8, comes from Google, is for Chromium-based software like Microsoft Edge, Google Chrome, Apple Safari, Couchbase, Node.js, etc. You got SpiderMonkey, comes from Netscape, used in Firefox, Thunderbird, the DBMS React or MongoDB, for example. You got Hermes, which is pretty new, it's from Facebook. It's used in React Native in the new engine. You got JavaScript Core, originates from KDE, an open source interface for Linux, and is used in WebKit in the older versions of WebKit 2. But there's a difference. Each engine has its own implementation of caching and exposed API. So what you find in one of them could not be exposed in the other ones. So, of course, as of today, you might be mostly interested in V8 because of Node.js. So this is just an excerpt from the V8 code, still coded, in C. So this is exactly what you find in the V8. You got the source here, and you've got this bytecode thing, with a full use. And if you just go down this, you'll see, if you just go to the opcodes of Firefox, SpiderMonkey, and if you go to V8, you'll see the bytecodes, they are here, and you got a full list of them, okay? Also, it's worth a few things mentioning PHP. I'm gonna make a small pause on this one. If you just focus, magnify what the PHP case is about. PHP stores what is called OPCodes in OPCache. There's a cache for OPCodes, okay? The arrays inside are immutable, but shared between processes, which means you could have the same thing reused by several processes of PHP. It's basically made of pointers. It avoids repeated code compilation since PHP 5.4. It can be checked through OPCache get status, which just returns a huge array of everything that is currently inside the OPCache. And you can reset it through OPCache reset, which just basically erases all the things. I found out a pretty cool development graphical user interface on this GitHub things. It can be integrated in Symfony with service action, uses React.js and PHP 7.1+, and it's pretty good to visualize what's inside your cache. If you want to use it, it's pretty cool. And if you just want to see what your scripts are generating, I just recommend not doing this on any script that goes over 30 or 50 lines of code, because as you can see, it's pretty verbose. So you just go to your PHP ini or the command line argument, you enable the OPCache op debug level, it just echoes all the OPCode in CLI instead of just using it. It's super hardcore, and if you do this, OPCache debug level, and you set this value, it's going to dump everything. So for example, if I just take a file, your file.php, whatever, I say echo hello world and echo 2 + 4, you got this thing. So this already outputs all this OPCache, you know, and of course you got the return because everything that's being computed in the middle time is going to be in that, okay? Also, don't forget to configure your OPCache. And also, yeah, you have to enable it, because we all know that happened, right? We're just wondering why it's slow in production, and then suddenly you realize OPCache is not really activated. So let's dig a little into that, you know, because we know we all checked the OPCache configuration and we never fully dived into those weird numbers and parameters. So like, what is this wizardry? So let's demystify a little, okay? So first of all, you have to enable it, then you have to tell how much memory it can take and how many scripts it can store, depending on how many you want to load. Then you have the validation and revalidation policy. Could be about timestamp or frequency, you know, in seconds. You can say how much memory can just overlap when it's going to the top, and the maximum strings buffer size, you know. So this is a few parameters you should just take a look on, and also it's free to you. It's up to you to enable it in CLI mode, because you shouldn't do this all the time if you want some batch processing, I would say, that is supposed to be really real time and you want to see it work, you know. There's no real interest in caching when you are in CLI, but for some reasons you might have, and you might want this too. And also you can use this with preloading. I won't talk about preloading here because that would be a whole talk by itself. Just remember, this is a globally accessible and preloaded in RAM cache script plus cache script that allows faster execution chain starts. Spoiler, it works. Spoiler, you can make a lot of mistakes here. So there's a great talk by Yashim Kudnis at PHP UK 2020 about preloading, and go check it out if you want to speak about Symfony. I think Nicolas Grekas just did a super good presentation about this last year too. So this is how it works at the moment. You know, this huge thing here, you know, you just think of something like GCC for compilation. First, the language has to be lexed and parsed. The PHP source gets compiled into OPCodes, and those are internal instructions. Then they get executed on a virtual machine, and the VM transform C code in machine codes and executes it, okay? And basically what a just-in-time compiler, this was ahead of time that way, okay? This was what we call ahead of time. You know, this is time of execution, this was done ahead, okay? This is just-in-time, which means we basically have just-in-time, a JIT compiler. It just allows you to direct PHP code can be compiled into machine code to the CPU. Just-in-time is basically a gradual way to try to figure out what your program is doing and going to do, and to turn PHP code into CPU instructions directly, more or less. Theoretically, removing the in-between should be positive, but that's more complex in reality. Should bring around 10 to 20% performance improvements on the average. Of course, if you do heavy maths calculations, repetitive calculations, and batch processing, you're going to save a lot of memory with that. And also, another super classic part of your apps, you need to cache. Actually, it's done for you normally, but that's quite low level and super important, is the Realpath cache. Every time your high-level app resolves a path, like including a file, for example, it calls the language structure that does so at a lower level. The language is usually C compiled interpreter that has an internal stat or lstat or fstat function that usually calls the system primitive with the same name. The process goes through reading the file tables and recursively resolving if the traverse path exists or not, and if it's intermediary paths or directories, okay? So you find them in pretty much all the languages, as you can see. You just got this in Java, in Python, whatever you want it to be. It's just everywhere, okay? So when you just want to resolve, I don't know, if you want to resolve a path that's /1/2/3, you have to resolve /1/1, then /1/ then /1/2. But you have to check everything in between, okay? So let's take a look again. And with PHP internals. So this also uses the buffer cache, by the way we mentioned above, okay? So it was introduced in PHP 5.1, and it's used by all the functions in PHP that basically deal with files and directories. Everything that is dealing with the file system uses the Realpath cache. There's just on Linux, on any Unix thing, you know, it just avoids reading the inode table, if you remember that, which also uses buffer cache, by the way. Unix also has its own internal cache for that. So when you develop today, you are using this solid architecture principles, you know, and the S stands for singular responsibility, which means you're going to create a file for a class. So we now face many more files that we're used to. Hello, autoloaders, it's your time. So remember, this is process bound. So if you got X processes, you got X time consumes on disk. Okay, we got lots of things to share in between processes. Okay. And there are a few details you might be curious about. So you can just configure on PHP the size and the time to leave, how long entries should be considered fresh. Okay. So you should increase this on production, for example, if you don't deploy all the time and if your entries don't change very often, especially if you don't generate PHP files. You can use this function, Realpath Cache Get, to just see what's inside. You're going to have a lot of entries. It can be super high, actually. You should just make a reasonable level only. So if you use a framework, now the default value have been increased. So as I say here, by the way, if you've got large frameworks, you're going to increase this. So if you use Apache, you should avoid npm pre-fork and mod PHP. Actually, what are you doing? What are you doing? We're going to talk about this. You should just use PHP FPM and npm event, or even worker for specific reasons. You know, this really helps Realpath caching because Apache does this instead of PHP. That's way better and way faster. You put these options in automations and continuous configuration when you deploy them, so you can refresh them. So every time you deploy, you can ask your Docker script container, the CI integration containers, to just wipe out the cache. Okay. So if you want to estimate this on a 64-bit CPU, you know it consumes 56 bytes plus the character count that is resolved in path. So /1/2/3 makes 6 plus 1. So the size, PHP, remember, resolves every resolved served path, like I just say, okay? So it needs some warm-up after wiping, and the TTL, should be a few minutes. It's just sufficient, but you should just do it. And if you have larger frameworks which consume a lot of files, for example, it's not close to what Node.js does, but it's still NPM does, for example. But you got the idea. It's lots and lots of files, actually, so you should increase that, definitely. Just go check it out and see if it's saturated on your machine, okay? And so what about the rest of internal caches? Well, there are many other internal caches that we could talk about, especially when your language embeds external components. With PHP, you could talk about Sodium, PCRE, ENTL, ICU, etc. All these things are not part of the language. They are just incorporated into the language. You know, when you download PHP, you have this, but this is another open source project that uses its own cache, okay? And yeah, so if you just, for example, use Python, you got the functools module, you see that, and what I mean inside, you got lots of components that go inside, okay? But language caches are not the only thing you can use on your own working machines. There's a lot of more stuff you can cache, whether you're on the same machine or another one. The best way to kill an app first is usually to ask anything to your databases, or using a rocket launcher on your server. But that will be another talk. You can almost be 100% certain if there's a bottleneck somewhere in your app or a blockage that prevents scaling up, it is at the database level. I just recently completed an investigation on a slow system, and guess what? The guilty was the database. So thanks to the CAP theorem, your problem will be different depending on your DB type. So the short version is, if it's relational, you'll end up with read problems and joins and relationships like joins, you know, and trouble and horrifying stuff like grouping, filtering, ordering. That's just nasty. And if it's not relational, you'll scale up more easily and sacrifice storage space in favor of query complexity, but writing and reading will become more complex. So for instance, if you don't understand what I'm talking about when I say CAP theorem and stuff, you got Apache Cassandra. I did a talk on that, so it's on my YouTube channel, by the way. So Apache Cassandra puts all the key space structures and the caches in RAM to further improve performance. We're gonna talk about this in a minute, but yeah, I did a whole course, online course of it, 3 hours and a half. It's pretty long, but it's complete, you know. So if you just got interested, just go and check what I'm doing. It's good. I'll be glad to have your feedback. So usually you won't have to go too deep in DB caching yourself. Though it is a science, most DBMS, especially the most used and maintained ones and the relational ones, are optimized and well thought. Performance is part of their design, so they've been here for ages and many people use them. So most DBMS just do this for you. But some DBMS use a query cache or a result cache. The first one avoids recalculating the query parsing like SQL, or simply the algorithmic optimization like MongoDB does, okay? So you got your app and you got this database that is inside your DBMS, okay? So you just make a query, you miss the cache, you go to the database, computes the database engine, the runner, what we call the runner. It just runs the database query, you store it into cache, and then you store it. And the next time you go for that, you just dodge the second part. So I'll show you 4 examples, 2 of each, of what databases can do. See that the mechanics and problematics are close to the same. So long story long about MySQL. So it's actually called MySQL. If you just get to the history of it, the guy who just invented those 2 systems, brilliant guy, has two daughters. The first name is called Mui, it's a Norwegian or Swedish name, I don't remember, and the other one is called Maria. So those are the daughter's name, okay? So they just removed the cache system currently in MySQL. They're encouraging the man-in-the-middle software. The query rewriting has been there still for optimization. MySQL now supports pre-parse rewriting plugins. So if you go to MyCNF, you just don't do anything with MySQL, but in MariaDB, the latest version, you should still go to MyCNF, the config file, and you choose how the cache is going to be called. So off, on, or on demand, which means you have to say use cache on every request on the query you're going to do. You can set the limit, the size, and if you want to strip the comments before caching. Also, you can check the status in MariaDB. So you just go you do these queries, you're gonna see how it's consuming right at the moment. And MySQL still has the pre-post statement and program caches. All the databases had this, and the engine-specific caches for MySQL and InnoDB. But you need to adapt this to your environment. So you need to worry about how much RAM you have, how much you use it. Is MySQL, is your database the only thing on your system? What are your query structures? What are your frequent queries, etc.? So remember, all the query analysis for caching are case sensitive. So everything you change, any character, could be a different entry in cache. So could be slowing down actually. So the first thing also you need to remember before everything is that you cannot cache everything. Not all queries are candidates for caching. Actually, it's not only that the right queries cannot be cached, this is of course simple to understand, but you got many query and many keywords that cannot be cached. So you got a full entry on the documentation to just learn more about that. Okay. So the short answer is use ProxiesQL and you're done. That's just the man-in-the-middle software I've been talking about. Okay. So about PostgreSQL, this is different. PostgreSQL can still cache data in tables, indexes, and query plans. Like I just said, every DBMS is going to do it. Uses RAM for fast storage too. Stores on memory pages, by default it's going to be 8 kilobytes. Each page contains tuples and metadata, and when the query is done, PostgreSQL copies the relevant tuples into the shared buffer caches. So it's just actually, when it thinks it's done enough, when something is done on a query, it just puts this into the shared buffer caches. And then it uses the least recently used policy to evict the older data from cache. Okay, so the older used things get evicted when the new one comes in. Okay, so also PostgreSQL uses checkpoints to determine when to flash the disk. This is a recurring tempo things. It just checked that it needs to cache or not. Okay, So you still have access to some configuration in the PostGreSQL.conf file. Like you can choose the shared buffers configuration memory. You can just go on your DBMS inside the query console to just see this. You select the hit box read and the hit box hits to blocks read to just search for whatever you want it to be, and you're just going to see it, okay? And of course, like I said, on those two tools, PostgreSQL and MySQL, you've got scripts, little scripts, usually written in Perl, that you can download and use. They're just going to analyze what your DB is about, and they'll tell you if some configuration is optimized or not, okay? So same answer, you just use intermediary things like ProxiesQL or PGPool2 or whatever you want it to be, okay? So about MongoDB, for example, which is a non-relational database, it does not use results cache. MongoDB's got a configuration file in MongoDB. You can just it also does checkpoints just like PostgreSQL. The data is cached in RAM, but it's done every 60 seconds or after 2 gigabytes of written journal data is done. So written journal, it means whatever MongoDB has to do, okay? This is the actions log, not the data itself. It just means I have to do this, super verbose. So you can just, again, use query cache pan. I just told you every single DB has this. You can try to change this, but it's really not recommended by, actually change anything in MongoDB is not recommended. Is what they said. The Wired Tiger, the storage, okay, Wired Tiger is the storage engine of MongoDB. It has a configurable cache size in gigabytes, but it's just mostly informative. It's not something you're gonna change, It's just going to be determined by, I don't know, 50% of your available size space, it's just what it's going to be. So MongoDB is going to be pretty much straightforward. You don't have to do anything. And for example, if you use Cassandra, that's another story. This is a schema I use on the other talk I was mentioning on the course I make in Licence Professionnelle in France. This course is also available on YouTube. Check it out once again. Self-advertisement. Same here, Apache Cassandra uses memory as a buffer to make the I/O fast. And it also keeps tracks of data in a specific table, so it keeps a cache of frequently recently used keys. It's the same for rows. It uses mem tables as a temporary storage because the disk storage is immutable, so the write storage can be pretty intense. So writing the storage can be pretty intense, actually. So also it stores recently frequently used partition keys to better know where to find the data. It's distributed, so the data could be on another node, on many different servers. So yeah. And one, but not the least, thing what I wanted to say about Cassandra, in a glance, this is really lightning fast about a super complex DBMS. Cassandra uses Bloom filters. Those are super fast algorithms to determine if a requested data is not in a given table. This avoids 100% useless searches. It's just like if you remember the Einstein-Rosen bridge, like you don't even have to travel. Like, why would you do if you just compute it? No, don't compute it. We already know it's going to fail. So don't request, just return null, like an empty result set, okay? So that's Cassandra does, you just got this data coming in. Like I said, you got the commit log, the journal, actually, of everything that needs to be done. Then Cassandra stores it into the mem tables, which are the temporary used, most used reads and writes, okay? And then when it got time, Cassandra pushes this to the SS tables, these storage tables, the hard disk storage tables, because this is a super long process. This is actually immutable, so it contains gigabytes and gigabytes of data, if not more than this, actually. It's going to take a super long time. So that's what the people are going to be, okay? So yeah, that is the problem with Cassandra. And also, in addition to these caches, you can have a third-party cache that is not inside your app. This is just what we described, but on another server, okay? But to you, it's seen as a usable, non-pilotable cache in your application, And you got this very often on web services, for example, You can have third-party caches that just are the same that what we just saw, but they are used by some other providers, like in product information managers, customer relationship managers, the master data managers, the search intelligence, the enterprise resource planning, all the APIs out there, they all use their own caching system. This counts actually, because if you use an architecture that relies on web services, your web services can have a cache too. Okay, let's go a little higher in complexity, and this time we'll add caches that we can delegate to another piece of software on purpose that is not part of our initial stack. All right, let's go. The first one we can use is another DBMS as a cache, not solely directly store it to disk. You know why? Because they can handle disk better than you do, and also they can use super fast in memory storage. So the most common ones are REDIS and Memcache, Memcached. So, for example, if you use PHP, this basically replaces the native file system storage reflex. Like, where should we cache? Where should we cache? Just put it on the file system somewhere in a cache directory, okay? But it also works with mass storage, like MongoDB or anything that goes with PDU, actually. You can use another database to store your cache. Because if storing into the database is a pretty fast process, spoiler, it is a pretty fast process, then what is the use of making a whole calculation? You can also use the same database to store it, you know, that's pretty good actually. But yeah, usually that's slower than the native disk storage in the end, so yeah, but you can use any external adapters, like you can have your MySQL database that's making calculations, and you can store the results into the same database. So all the web software have their cache implementation, internal, delegable. So for example, Drupal, since the beginning up to Drupal 9 so far, has it natively templates and modules are cached, you know. WordPress has several cache modules like WP OPCache. Laravel support many cache configs. You just go to config/cache.php. Like Memcached, Redis, DynamoDB, and relational databases. Magento, the e-commerce software, has its own cache system, the file system, database, Redis, etc. And Symfony, for example, currently has those and supports, of course, as many cache pools as you like it. So you can store in different places using different providers at the same time. So each of these solutions here has their advantages and drawbacks. But also each manner of implementing and running caches has its own. So be aware that not everything is a great idea here, but yeah, okay. So let's have an example with PHP plus Symfony and Redis on another side. So first you need to use a PHP extension that brings Redis connections and support, like PHP Redis. You just got many of them actually, you got several of them. Then you just create a pool. That's good. You create a pool, not to dive in, but you put your things into. You tell which adapters it uses and the orders in which it's going to have to use the cache pools, okay? So you can create a custom extended provider with whatever special parameters you want it to be, like retrieval interval, timeout here for Redis. And last but not the least, you tell your application how to connect to it, mostly using a database, a data source name, okay? So you just say this and you got the connection here, okay? You just take this into your local parameters that you're not gonna share, okay? So then you have a specific CLI stuff to see your pools. You can watch them, you can clear them one by one or everything, okay? And all you need to do is a little Redis configuration then. So you just, like how much RAM it can burn, because Redis will burn your RAM. When you're caching, you need to know when the values should go away, because they're not gonna stay for a long time, because if you have 100% values in your cache, then you don't need to cache. You have a permanent storage that's just faster than the older one, you know, it's just pretty efficient cache actually, but you're not really caching, you're just storing, okay? So there are different strategies for that, we'll cover that later on. Just go with LRU or LFU if you want to try this with Redis and PHP cache system. Also, you can encrypt the cache items. Don't do this unless you really have to, but Symfony actually supports that, for example. And I could give you another example, you know, with, for example, if I was to go on Laravel, this would be the same. You would just put a client, put a cache, you put the host and the equivalent of the DSN here, and you would just go and you would go cache. And if you want to leave PHP for a moment, you can use this in Django. This is Python. This is just Python code. And when you define it, you just go to the settings.py file, and boom, you just got a cache, you got a backend, and guess what? You got the equivalent of a DSN here, and you say how Django is going to cache your things. That's just the same, okay? And just a side note before we go further, when I'm talking about Symfony, Redis, and PHP, etc., you should just use Redis to store your sessions too. This is not about cache, but I want you to just mention that. You just pause the slide later on if you want to do this. Those ideas here usually go well together. So if you got Redis ready and Symfony up to the challenge, you should just make those things work, okay? So that being said, there's another thing you could do. You can use component-specific caching, like templates caching. This is useful in MVC because the V stands for view. And the view processing is different from the modal processing, and it's not transparent. It has a cost. So if you take, for example, a hot cache reset --no-warmup on Symfony when using Twig, you know that the factory part is already cached. The framework part, is already cached, but Twig, the template engine, has its own cache because it's a meta language that needs to just basically not transpile, but compile down into PHP. So you can change it, disable it, or you can even use Twig directly. This requires actually Twig extra bundle and Twig 3, I think, if I remember well. So this actually allows you to handle some cache entries directly into the templating language, which is pretty cool actually, okay? So yeah, and you can also disable it like that, but just be careful with that. So what we've been doing so far since start is called memoization. And no, I didn't miss an R, it's memoization. Memoize is the base caching process. So you check and return what is stored or you store it. That's what the first schema I told you about, later earlier in this presentation is about. So this is just like we explained about adding a key value or a hash storage to an intense calculation results, and you store them. When the output is expected to be the same for the same given input, which is what we call idempotent, okay? But memoization is just like caching at the unit level. You do this for a function. So when your prototype always has the same value, when it's idempotent, you should just try memoization. It's actually working on any function, So it really becomes super useful when you got expensive functions, process, methods, whatever you want to call it. And when they get more and more expensive as the values grow, okay? When you got like Fibonacci, factorial stuff, which is the more you calculate, the more it gets complex, okay? And also which can reuse previous calculations that also can be part of a cache. So here is a very basic example with JavaScript and something you all know about from school, factorial. Woo! Remember that? Factorial n as multiplied by n-1, n-2, n-3, etc. up to 0, and factorial of 0 is 1. Okay? So it basically reuses lesser factorial calculations as a way to calculate its value. So when the numbers go high, you might seriously need caching. Actually, your main problem will very soon be the registry size. Yeah, the 64 bits are going down pretty fast because factorial is brilliantly going fast in maths, So if you do this, you just got this function here that calculates a factorial. So if it's 0, it just returns 1. Otherwise, if we just got this in cache, we're just going to say, hey, we hit the cache. This is not a one-shot memoization, okay? We could do this in one function. But I want you to split all those things. So otherwise, you just return the number you want to factorials multiplied by the cache that you have n-1, okay? So you just check that the previous calculation, the lesser -1 calculation is, otherwise you're going to have to calculate through all the previous calculations, -1, -2, -3, -4, -6, etc. So whatever it's going to be, at some point, you're going to hit this cache. And even if you already calculated 2, 4, and 6, you're going to have to go for 6, 4, 5, 3, 2, 1 if you go to 7. So whatever you're going to do is being useful. So then you've got that memoize value function. So you just got the function that is being taken as a parameter, and you have to memorize it. You fully integrate into the cache or the factorial, but we could just not need the wrapper call here. That's just a dumb example, okay? A silly example of memoization, but I think it's pretty self-explanatory. So when you just call the function here, you take whatever arguments is passed and you say, do we have this in cache? No? Then we're going to return the cache. So this avoids actually calling the whole function. And then otherwise you say, nah, we missed the cache. So what we're going to do is call the function that applies a manual way of calling things in JavaScript. And we're going to say that we're going to return this value and put it into the cache. Okay, it's just the same memoization I think I show you in the first slides of this talk. If you have this and it's fresh, there's no freshness here because this is permanent. You know, the calculation of my of 2 times 3 is not going to change from one execution to another. So we could have a little freshness, but at least we don't have to care about the freshness. So if we chain us a perfect, okay, it's a perfect sequence of calls. 0, 1, 2, 3, 4, 5 is the ideal case because if you have 5, you have 4, 3, 2, 1, 0. If you have 4, you have 3, 2, 1, 0, etc. So you're going to make a cache miss, then all the cache are hits. Okay, so if you do this, if you call factorial 5, it's going to say, hey, we got something in cache for 0, 1, 2, 3, 4. I mean, actually, it's going to go for 5, 2, 3, 2, 1, etc. The reverse down. And it's going to say in the end, well, I got everything. So factorial 5 is 120. Okay, this is how you use the memoization. Okay, this was just a basic, simple factorial thing that I just used into memoization just to say, can we use the cache? Okay, so let's climb another mountain. All right. Sometimes you don't want or you can't rewrite application. Actually, this happened on a mission to me when I was making this presentation. But excuse me, you can add a layer on top of your architecture, or you can sneak inside of it in between 2 components. At worst, between the result interface and the calculating interface, okay? So before we talk about what's next, just a reminder about web servers. You can see the current more or less accurately measured market shares. I suppose this is accurate. Most web servers can actually be one of your cache systems. Yeah, they do it. They can also handle other software responses or their own. When a system handles a request or response for you, it's called a proxy, okay? When a system handles dispatching and only manipulates requests and responses, or is used to obfuscate its backend architecture, it's called usually a gateway. When a system proxies requests, responses, caches them, optimizes them, prefetches, compresses, it's called an accelerator. Not everyone agrees on those terms, but since many solutions implement all uses, you don't really care. Just like fusilli, farfalle, scapelli, spaghetti are, in the end, noodles. They are all in your stomach, or maybe in mine, because you were not fast enough. So reverse proxies are also called surrogate caches or even HTTP accelerators, gateway caches, like I told you. Like I just said on the last slide, it depends, okay? It depends. They basically filter, clean out, prepare, simplify requests and responses, and store the latter, okay? They are designed to be shared caches, usually. And they can do more stuff than this and can be combined with other systems. So you got the pretty much usual players here: Apache, NginX, Squid, Lightspeed, VarnishCache, etc. And they can also provide lots of things. You know, you can pass the results to antivirus. You can compress the headers. You can go for load balancing. You can anonymize the request. You can actually manipulate everything you want it to be. Okay, so the subsequent backend can be behind a firewall to increase security, okay? So how do they work? Well, basically, you will simply suppose you have an inbound HTTP request. Let's just talk about HTTP for now. That's coming in. Instead of sending it to the backend, after your DNS resolution process and going through the internet oceans and the internal moat, dragon, boiling all defenses of a target internal network, you direct traffic to an intermediary software that will handle it and forward it. This is a cache and you forward it. So for the first pass, the request, of course, gets simply forwarded, misses the cache entries, and it tells the response, then it just gives it back from the backend and it's transmitted to the device that generated that request. So then what happens to the subsequent following times? Well, the request is only hitting the proxy, supposedly hit the cache, if the rules allows it. There's a copy of the response immediately gets sent back and is being read from the cache. And voila, you didn't hit the strong calculation device, you know, backend stuff here. Like a Java server, for instance. Oops, not mentioning it. So how do you set up those things? Well, let's see a few famous examples. So first, NginX, straight from the documentation. So you put the path outside your any server block. You have to do this in an HTTP block. It's just better. Okay, so this is a server-based parameters, okay, calculation. Then you set up your cache directory here. The levels here indicate the character count. Like it's going to be /cache/ your directory /dir here, dir, or /a/25, for example. Okay, 1 then 2 characters. Okay. Inactive is the expiration time since it was last accessed. Okay. The key zone is the memory key name and size. You want to do this, and the size is how long it should be. You got here, for example, the 10 megabytes zone, and this is the maximum size that your things should do. Okay, so it should take. This is the maximum disk space. Okay, this is the RAM space, and this is the disk space that it's allowed to take, if I remember well. Okay, so you also tell NginX what to do if the backend response is responding with errors, but you still have stale cache entries. You know, while the backend is burning, while something is burning, this is super fine. You can still choose to say, all right, it's just good, just serve the cache, and maybe the backend is on 500 error for some reason, but you don't care. You can still keep on serving for a few minutes, and then you're gonna say, well, I'm gonna have to do something about this. Maybe someone tried the rocket launcher things I suggested a few slides ago. You didn't follow my presentations on rocket launchers on servers. That's a whole talk. And you can also tell NginX to add a custom header, and you can also tell it to ignore specific headers, like this one are not concerned, they do not get cached. You don't store this, okay? These don't get stored. And then you link to any directive in your cache pool. You tell the cache which HTTP response you want to use. So, and how long it should keep each of these responses. You can make any number of these lines. So be careful, we're going to talk about that later on. You should never cache some headers, some HTTP response codes, you know, and some headers too, and some HTTP response codes. That is super important, okay? And then which condition, not empty, not 0, to check that, otherwise it will not be cached, okay? So first you say, do we have no cache? Do we have this variable here that we just use here? So close as code, you know, NginX configuration file. So you then say which conditions are dodging the cache. For example, if you find the PHP session ID cookie in your caches, you just avoid caching, it's not good. If you got a query string, you might just want to avoid your query strings. Maybe they're not cacheable. Some of them could be, some of them could not. Okay, and then you have your rest of the configuration here, okay? So please note, even though this is not about performance only, we talk about Symlinks cache and Realpath, and we just use Realpath root here in this configuration. This is really improving performance, by the way, in NginX. So this makes actually a short version is NginX resolve the path instead of PHP FPM, just like I told you about Apache, okay? And you can also mount the cache directory in RAM, so you can make a temporary file system and use it in RAM. So if you do this, it's gonna be super fast actually, okay? So first with Apache, the equivalent, you have to enable some modules, these ones, not only. So caching enables this cache and caching in memory. And then you can hit for proxy request. You're gonna have to use this too, because otherwise, for instance, you might have virtual hosts configuration too. It's just more convenient to have a virtual host here. And then after some enabling, you know, you have to configure your things. So you just say the same thing, you know, you just tell what the backend is and which IP you want to use to hide the backend, you know. So this is how you basically configure a cache in Apache, you know. This is really easy. And then just remember what we did about NginX is just going to be the same. You have to say what's going to happen with default value on the expiration. You can say to handle some specific headers. You can ignore some headers. Remember, it's just the same thing we did. You can add, again, the custom cache headers. It's just exactly the same thing you find on NginX. Also, you can disable from some URLs. That's another way of saying I want to accept this. You can also tells which headers, paths, conditions you want to ignore. So you add a custom header too, and you can also tell it if you want to use the cache disk file, if it's loaded, where to cache it. If you remember these things on Nginx 1 and 2, you just got this, the levels and length. So this is going to be the number of directories. Here it's going to be 64 per 64, so 4096 cache subdirectories, for instance, and you do the same thing. It's going to break down this into chunks, var cache apache your vhostname /a/25. Okay, so it just reads a different way in the end, but it's just the same. It just goes to caching. And Varnish, for example, could be a whole talk by itself, because Varnish is just dark magic on whatever you want it to do. What VarnishCache is a wow thing. when you just receive and transmit HTTP responses and requests, Varnish can handle and modify everything. So basically, it's a piece of software that allows you to rework and alter every HTTP request. You can clean, improve, modify whatever comes in as a response, And finally, you can use it to cache it, store it, and later check your cache through your own rules. For that, you essentially in Varnish need to overwrite default configuration and rewrite little pieces of code that are called subroutines that are written in a language called VCL. Okay, this is a VCL accept. Okay, so usually you'll clean requests from varying headers on VCL receive here. You do the same for the response on VCL deliver, and you can check when you can hash the request, look up that thing, or simply pass. Okay, this is whatever you're going to do with Varnish. Okay, it would be more complex to explain everything with Varnish. Then, what happens when you realize that most modern applications use about 99% session independent response body, and around 1% that depends on a private session. Typically, this is any e-commerce website that just has a basic non-user specific price rules display. Every one of them fall under the cases. That small exception on the top right, the welcome John Doe on the top right on the header bar, that is just along with a disconnect button that no one ever clicks. That is, by the way, the saddest link ever, along with a legal link on the bottom that no one wins. Well, there was an idea, Stark knows this, called the Avenger Initiative. Wait, no. There was an idea. Oh, the edge side includes. Yeah, the edge side includes and the server side includes initiative. I had just old memories of a movie. I don't know which one, but you're going to find it. It's part of the W3 spec that's originated in 2001, and it defines the possibility of decomposing requests through reading the response body instead of thinking response as a simple payload. So it drives HTTP behavior through the response, which is kind of magic, actually. For that, you need special sequences of text. So what do you find in a web response? HTML. Yeah, you find HTML. So, except those tags are not part of the HTML5 doc type reference. So if a browser finds them for whatever reasons, it will just ignore the contents. So when the intermediary elements find them, yes, that's HTML that's only intended for the intermediary elements. That's quite hard to realize. They pause, they make a sub request, they consider what's around this sub response as a single response too, which is you have HTML, part A, B, C, D. If B, C, D are sub requests, they will do sub request and then it will be cached differently. Okay, why? Because now we got a global response with everything that's shared and multiple sub responses that can be independently cached. So your 99% HTML will be cached for a long time, and the 1% that will go into a much lighter sub request that takes way less time to execute and consumes way less resources. So in order to drive that mechanic, the spec adds a few tools: inclusion, like HTML inclusion tags, variables and conditions, of course, to do super basic algorithms, and error handling. So how do you implement that? How do you implement edge side includes? They are called edge side includes. By just writing down HTML code first and picking a proxy technology that can understand it. So, like I just said, you need to update your HTML code. So you use this. This is part of your HTML code. The ESI processors try to fetch the src attribute here. Then if it fails, it goes to the alt attributes, and then it returns an HTTP 404, not found, unless the on error here is specifically set. The ESI would be replaced with nothing. And then you've got this, we say, what happens when this is not supported? So the remove tag here works on browsers. So they will ignore the invalid HTML, they will pass everything, this is not included, not included, not included, not included, and they will just include this, and you will just see a paragraph. Ooh, magic. So, and of course, you cannot put another thing of ESI block inside the ESI remove tags. Don't think about such thing, you evil being, and stop rewatching the Inception movie. So far, variables could include HTTP accept language, cookie, HTTP host, HTTP referrer, user agent, query string, etc. So just remember, don't include variable in just like any HTML line. It's just standalone block. Okay, you have to do this like that, and this could be used and interpreted by the ESI. Okay, so imagine you have much more HTML above this and below this. You have the whole things that your page is shared between all users, and then inside this you've got this little thing that says if you are connected, if you have a cookie, then just fetch for the hello Mr. whatever you want it to be and display and insert it. It's going to be super more efficient if you do this, okay? So second, you need to update your proxy software, because yeah, that was on the backend, okay? The first one was on the backend. This is now on the proxy software. So how do you do this? Well, you just illustrate it with VarnishCache, okay? Just check out what it is and that it supports it and go for it. You can change your subroutines, like I just mentioned 3 slides ago. It's on the official documentation. Don't panic. You will panic when you read it. You have to activate your ESI supports and tags, okay? So you have to say, I want to use ESI. And a few more things. Varnish claims that content substitution based on variables and cookies is not implemented, but on the roadmap, so be careful with that. And also, Varnish can actually work with ESI on non-HTML content, like JSON or XML. Woo, it's pretty cool. And also, Varnish cannot use HTTPS sub-content. It will treat any sub-requests with HTTP only, which is okay if you are on the same host, okay? And one more thing about those reverse proxies, as I said, it can be pretty much any piece of software in your call chain. So why not have it directly inside the backend application? Yes, you can have it part of the backend application. So you can ask your app to handle the request before it goes into your application logic. So you see, it's still better than calling a whole response build, like fetching third-party web services, DBMS, or heavy calculation process. It might be redundant with some other reverse proxies that are going to do the same caching on the same thing based on HTTP, and it's going to be shared caches, but it could be used. So for example, if you use Symfony, PHP framework Symfony, it has an embedded version that could be an internal reverse proxy. It behaves like you expect it to. It just supports ESIs too. It stores responses into its own cache, into the application cache directory. It's usable, but it's not recommended to rely on this stuff. But if you really know what you're doing, you can use it, okay? So you just also, it also supports the non-standard method purge, but it's not standard, but you can use it to purge the cache if you want to. So you post you send a request that is using the purge keyword and is method. It's going to be cool. It's going to work and purge whatever is in the cache, okay? You should just prefer an external reverse proxy, but at least it works, okay? Then, to close this part, one last chainable cache you can use. I mentioned it a few slides ago. You can use a database layer cache. So most of the time you need to cache your query reconversion into instructions, your data structures and statistics, and of course the return responses. So adding a cache layer in between your querying gaps and your DBs also helps if you have multiple DB servers on the backend, like orchestration of data. If you have multiple apps on the front, like multiple applications that share one database backend or simply load balance front ends. Okay. For instance, when Redis is used as a cache, often it is handy to let it automatically evict data as you add new data. Okay, so this is a good candidate, but you need to pick up an eviction policy to make sure your applications are not parasiting each other. Okay, so you can use an eviction policy. We talked about that, So we need to first identify what's going to be read repeatedly. You're going to be required to say what's your data format, because if you have like complex SQL structures in database, you just select where, join where, whatever you're going to be. You don't want to replicate this database structure into your cache because it's going to be the same slow, it's going to be the same thing. So you have to think again. You have to say, can I just do key value where key is the hash of my request and value is what I found out, and then you got the cache entry date when it was fetched or whatever. You just got it super fast. Okay, so you have to think that your backend data structure is not going to be represented into your middleware database layer cache. Okay, and then you have to set up how long these entries could be lasting. There's a pseudo French list, it's going to be more or less fresh, and find an eviction policy. Like I said, first in, first out. That means it evicts the oldest entries. The newest entries are most likely to be reused. You got the last in, first out, which is the latest entries are going to be evicted. So the older entries are most likely to be reused. You've got the list recently used, the LRU. You're going to see that a lot in this talk, by the way. It just evicts the list recently used entries. So the recently used entries are most likely to be reused. What is recent is usually going to be reused. You got the most recently used, which is exactly the opposite. It evicts the most recently used entries. So the least recently used entries are most likely to be reused. And you got the LFU, the least frequently used, which just evicts the least often accessed. Okay, so when the entries are less accessed, they are more likely to be thrown away, and the most hit ones are going to be reused. So how does it work? Is basically about storing a count, a number, a counter of how many times it was accessed, and reset the counter from time to time. Okay. So what's the principle? Whatever you're doing, if you're storing things in a database, you will have to do reads. No one writes a DB to never retrieve data. I mean, the older ones retrieve. You remember those super heavy tapes with infinite backups that no one asked for, that were stored in a cupboard that was removed by bulldozers when the company moved? Those tapes, those super old magnetic tapes, where you were usually put next to the useless merch sent from partners that no one wanted to get rid of. You know what I mean, okay? So, and also the project documentation printed just stands next to these things. So here again, same stuff. Except we don't trade lives, Captain. We're trading SQL queries and result sets. So we send a query to the database through its cache, of course, again. And its cache sends it to the runner process, like I just mentioned a few slides ago. It's probably going to parse the SQL, if you use SQL, maybe you're not, maybe you don't have a relational database. It's going to parse the query to build it, even MongoDB does that. Then it's going to execute it against the DB, which is reading, writing tables mostly, or values, document, graphs, whatever your database is doing is going to do the same thing. And then that long process returns a statement containing the results. If it's cacheable, it's a cacheable query, and there are, like you said a few slides ago, many reasons why queries cannot be cached. Not only when they are not idempotent like writes, but most of them actually. So then you most likely get the results, and you simply store the results. And after your cache here needs clues to know when things are not fresh, like when you update values from a table that uses cache, okay? So your cache here needs some clues to understand how things are fresh or not and how to store it. So if it's cacheable, which is Again, quite unlikely, but it can happen. You get to store it. And that's what most database engines do. You write a buffer of tasks to your commit log, to your journal. So what you just never forget what you have to do. It's just basically like when you're going to the mall and you make a list of what you have to buy, except the database is never going to forget that damn bottle of shampoo, okay? Then the database commits this into RAM. Then eventually they will garbage collect what they have to do and flush all the temporary data to disk, okay? But as long as you have queries that can be cached, as long as they are not evicted, most likely the least used, oldest, or any userland heuristic you choose, you can keep up a fresh result in your cache. So they're going to be hit, they're going to be read from the cache and returned, and you never run the query again. So you just return that query again, just instead of going to through the same process. All right, so what happens if your application is already optimized internally and still reaching a critical use of resources, okay? What happens if you can't really go through those type of software configuration, or everything we've seen before is already checked? Well, then you can start using caches outside your application, outside your information system. For that, we're going to see that we have an external external third-party proxies or distributed systems at disposal. These systems, for examples, are mostly often known as CDNs, which stands for Content Delivery Networks. That's how they basically work. You store the final responses. It's really binary, it's just you read the bytes and you store the bytes, whatever it's going to be. It's usually distributed to reduce the time, so with points of presence all around the globe, and it's usually based on HTTP, the methods, the headers, what you want it to be, or sometimes more advanced parameters like geolocation, query time, etc. It's simple. You can do this in 2 steps. You have 2 steps to use them. The first one is delegating your network load, which means when your server is responding with an image, a video, a font, whatever you want it to be, is not doing anything else. Even though it's not really CPU intense, it has to be doing so. It's blocked. It's not using a lot of CPU, but it's blocked. So first, you want to release part of your network. You want to let your network breathe. So for that, the best way to breathe is not the thousands of requests by the backend, it's the thousands of assets. So everything that's static, CSS, JS, images mostly, videos, WebP, WebM files, whatever you want it to be, all those things are going to be super, super heavy load. So you want to delegate this. So you want to have some external caches that will handle that for you, because they are way more advanced in terms of caching optimization, okay? And then the second step is to say, all right, we're going to use the CDN to cache all the resources, including the dynamic ones, including the queries, the requests, HTTP requests that go through your backend, including the ones that could be sometimes connected. You're going to go through these CDNs, okay? So usually you end up like whatever I said, the cookies, like the session cookies, and you can have the custom cookie as a pass-through if you just want to debug or know what you can do in production, like passing a specific custom cookie you want to try, okay? And once again, those are shared caches, okay? And why are they useful? Why are the CDN useful? Well, it's pretty easy. They just save time and energy. They reduce network loads globally and locally, which means your network is going to be better. And also the global internet routing system is going to be way more optimized if they fetch those things that have super high bandwidth, better than your own local provider, okay? They reduce end user latency, which is really good. The people are going to get your assets and everything with milliseconds less. And we're just deploying 5G at the moment right now for these reasons. We're just reducing latency. It also reduces server loads and costs and open connections, which is really good. That saves, network consumptions again and server loads too. And also actually the search engine rankings are going to say that is better because the website is loading faster. So you're getting actually some return on investment on this. And also it is that is a long talk and it's going to be complex to say so, but it is probably green IT or greenish. I think it saves overseas traffic most of the time, which is really, really more expensive than what you're going to do by your own. I know those are super farm of servers. They are just like immense. They are whole data warehouses, data centers. They look like super huge things, but they are huge because they manipulate data for a huge number of people actually. So that's why they got this impression of being huge. But actually, I think it's still greener or greenish or something if you use them than if you do everything by yourself. And also, last but not the least, this handles denial of services, including DDoS, whatever it's going to be, and scalability much better than you do because they have security experts in a level that you don't have because that's their jobs and that's not yours. So what underlying mechanics would you consider to set them up? They all got documentation, but usually you just change your DNS, so you have subdomains or the DNS alias record for the apex domains, the top level part of your domain, not the top level domains, but top level part of your domains. And sometimes you just use a CNAME or canonical name as a fallback for other cases. But yeah, also you have to pick up a writer because you're not going to do this yourself, and there are many of them: CloudFront, Google Azure, Cloudflare, Akamai, Fastly, Ski, whatever. I'm not going to read all the things on the slide because there are so many of them. But don't forget to be ready for a backup plan because, as people once said, it's not cloud computing, it is someone else's computer. So you got to be ready for that. Even though they are pretty reliable, sometimes they could be deceptive, okay? And finally, last but not the least, this is the longest and last part of this talk, and then I will release you. As this talk is about the web, let's talk about the core caching concept that is defined for the web. So we're going to talk about forward proxies and HTTP caching, browser caching, and a little more before we conclude. Starting with the intermediary ones. When I mentioned reverse proxies, you obviously guessed that they were proxies, and they just rely on HTTP. We're going to see that in a minute. Well, the reverse proxies, you say they are proxies, but they can be also set up on the client side, and they're mostly called forward proxies. They work the same way, close to it, but they're on the other side of a network chain. And most software we already mentioned, like Apache, Varnish, whatever, we just say NginX, can do the job. That's pretty great, you get to reuse the same software. Most of them can do the same thing both ways. Once again, they are shared caches, which means all the users can be using the shared cache pool. This is an intermediary that is linked like multiplexing, for every people. It just goes, it multiplexes all the requests into one funnel, and it just funnels everything back in a linear way to the backend, okay? So this is what a shared cache is, okay? But they can be used in many ways. They can be used to filter proxies, sanitize, control, block, and generate network exchanges. This could also be a whole talk by itself, but one thing that is worth noting is that they can be classified into two categories. First of all, the proxy transparency is a criterion. There could be a common proxy. Here, the proxy addresses, the port manually configured in the browser. This thing when you just go to your browser and you say proxy configuration, you never use it, maybe you're in a company or you have super high security at home. You want to do this, okay? In the browser or in the system environment variables for the client. For example, you specify the IP address of port 1234 on the Squid server on the client. The second possibility is it could be a transparent proxy, which is a little harder to set up, but it's pretty interesting too. There is no need for the proxy settings on the client. Your browser doesn't need configuration. The proxy role is transparent to the client. For example, a web gateway device on an enterprise network is a transparent proxy. And about HTTPS topology, SSL encryption, and network topology, you can think of two types. The tunnel proxy, this is a proxy that transparently emits traffic. Here the proxy server specifically transmits the HTTPS traffic over TCP transparently. It does not decrypt or perceive the specific content or its proxy traffic, or if you just want to say it in one sentence, the client performs direct TLS or SSL interaction with the target server. And the second possibility is the man-in-the-middle approach. The man-in-the-middle proxy decrypts HTTPS traffic. Yes, it does. It does has its own HTTPS traffic. So it decrypts whatever your browser would do. It does the same, but it's not your browser, okay? It uses a self-signed certificate to complete the TLS SSL handshake with the client, and it completes the normal TLS interaction with the target server. So you means that how do you keep up HTTPS on both sides? Well, there are two TLS or SSL sessions that are set up on the proxy client server link, one on each side. Okay, so you've got one proxy HTTPS tunnel on the client side with the client, between your proxy and the client, and one between the proxy and the server. Okay, so it just basically gets decrypted locally, then re-encrypted and put back to HTTPS. So you don't see the difference. Okay, so that is pretty interesting approach I was mentioning. So again, how does that work? It's pretty straightforward. Some end user device generates a request and it either has a custom network configuration or even not. The proxy captures or is sent the request. It forwards this request or is sent the request. It forwards the request to the designated target server. The request comes back, possibly gets stored if applicable, and then the request just gets forwarded back to the initial device. Except this time, it's just about the whole network. It's just, you got this. Actually, this is the outside network, and this is a client network too, okay? And regarding the cache mechanism only, once the request is in cache, the proxy can send it back without querying the remote server. Okay, this is, I'm on the backend side. Okay, so when I say your internal network it means you are taking care of this one. Okay, you don't handle this. Okay. But if you are handling the proxy and you are the client, this is your network and this is an external network, okay? Just invert the sentences, okay? So, of course, regarding the proxy rules, which is supposed to be as the W3C HTTP standards say, you could do this or not. You could choose to fetch and cache or not. You can enforce it and say, I don't want to cache, or you can aggressively cache, okay? The standards are expected to be the default for both forward and reverse proxies, but you can do whatever you want, like rewrite them completely, pass them to a firewall, have special security policies, etc., or any security device of software. Like you can just choose, for example, to block whatever porn site or bad site or malware site you want it to be, and you can say nope, this is not going anywhere. Okay, so I'm generating this and you just return a predefined response. You should not go to this website. Okay, so this just acts like a firewall actually. So let's see what those HTTP caching standards are about. That's the most important things you need to learn. Okay, those standards are probably the most interesting thing in HTTP to me. The best cache system is actually included into the messages themselves, like we saw in the very first slide on this talk when we said about what do we do on the internet. We make a request and a response, and we got small pieces of text. Okay, in that piece of text you got everything you need to know to handle caching on the internet, which is really cool, by the way. So is the best cache, because like we said earlier into the introduction of this talk, the fastest way to arrive is to simply never travel. So why would the request get out of your browser if it doesn't need to? That's why it is done, okay? Those standards, they were native in HTTP 1, improved in HTTP 1.1. They originate from this part normally. The RFC 1945 was published and adopted in 1996 by Tim Berners-Lee, thank you, bro, and Roy Fielding and Henry Frischtig. Those people are great too. Those three people just defined the standards. Essentially, the HTTP headers contain everything we need to handle those caches on both client side and server side. Okay, so the request generating device simply doesn't send the subsequent request if applicable, or simply receives a partial response, for instance. Okay, this simple principle provides a huge compression level of speed. You actually don't change anything like modern single-page applications would do. You don't charge anything, so you don't have to do a round trip. And also, not doing this round trip saves energy, bandwidth, improves performance, and once again, is pretty green because it saves the earth, okay? But what should you cache? Everything your application generates or receives has to be analyzed. The best plan is to cover the most used areas and to dive step by step into less used cases, okay? You should probably start with static assets. Like I said, those things are never or probably never going to change. I mean, like the image that are not generated, you know, not reworked, not recropped, etc. You should probably start with those assets, you know, because they change the less. Then think about those which change a little, okay? And then consider the ones that are the most dynamic in the end. But if you just go this way, if you just go from the easiest one that don't change to what changes the most, you will get very fast to a way better cache system, okay? The bad news is that you can, and actually you should only cache get and head methods. The good news is that get is the absolute vast majority of request made. There were statistics done by many people on the internet, and they found out that actually 50% of requests are actually get requests on an average application worldwide. So it's pretty good news actually, you know. So yeah. Not all the every codes, by the way, are okay to cache. In general, what is called a positive response cache, like 200 and 300, like I know what's happening. I'm the server, and you're good for that reason. You need to go there for that reason, or you need to move here. This has been redirected, changed, but I know what you're trying to do, okay? And some client-side errors, like not found, etc., can be cached, and the 501 is okay too, okay? So these are the only things you should cache. But again, that's get and 200, that's the most common answers, okay? And speaking about what you should cache, what you should not cache, you should avoid caching what's individual, which is, I mean by that, what is end-user specific, what is sensitive, what is changing every time it's called with random stuff, for example, or what is being concerned with cookies, okay? Whatever is concerned by cookies should be never cached, okay, most of the time. And unless they are not used, okay? But cookies could be passed but not used. That's a different story. And you should probably not cache any other HTTP code that were not in the previous slides, which is all those methods here should never be cached. By RFC definition, you cannot actually cache those methods, and the browsers will not do it, okay? And so all the other codes, the lots and lots of codes that I mentioned, that I did not mention on the previous slide, should never be cached, okay? So like 500 errors, like 304, whatever you want it to be. And also the non-standard method purge, like I mentioned, to empty the caches, the shared caches should never be cached, okay? You're not going to cache what is going to be emptying the cache, okay? So what's the mechanic behind this? Well, it's just the same as proxies and reverse proxies. It can be arbitrary. You can force caching anything outside of app context, but that's risky and aggressive. Or you can just follow the HTTP standards, which are validation and expiration. We'll get to that in a second, okay? So you just make a request, it goes back to the request here, you just get the response back, and then you store it, and you get the response again. So when I say that you do a cache miss, we actually hit it, but we consider it that it's out of date due to those caching mechanics, okay? So as you can guess, the outcome ends up being the same. The request generated by the HTTP component goes to the cache. Again, this is your browser, okay, usually. And it goes to the cache component, but both are usually inside your component, this chimera that is going to be named the browser, okay? It's not really a browser anymore, it's like a whole operating system behind a shortcut. Like, for example, Firefox, Mozilla Firefox currently has 137 components. Generating request is one of them. for example. So the outcome is the same. You get this, you fetch it from the cache, and you never go back outside. You never reach your internet box. You never reach whatever your modem is. You don't go anywhere, okay? That's great. And what if you put all the components we've seen so far? Yeah, let's do this in an HTTP chain, that is, on a single schema. Well, first of all, if your request goes the whole thing way back and through, you are damn lucky. Just kidding. We are engineers. We know what we do, right? But let's imagine that this works. Spoiler is this actually happens every day and you do not realize how lucky you guys are. So yeah, I hope you won't be afraid anymore to be super happy about the average 10,000 requests you make every day. Yeah, people do this average 10,000 requests every day. And some people design those systems to handle billions of requests like this every single day. Requests like this that just go through the whole cache systems. Believe it or not, the number of HTTP sub-requests per page has been growing every single day. But according to httparchive.org, it's been stable and slightly lower since the EU GDPR entered the game. It looks like ethics actually is network saving and energy and green saving. That's pretty good, actually. We're doing some good stuff when you want to. All right, so how does this caching thing work? Okay, is this a kind of magic, or is this real life, or is it just fantasy? Well, a little mix of both, okay? So you should have your engines caching the generated response. You can cache less. This is not really interesting. This is going to be more resource consuming, and you shouldn't cache more because this goes beyond the standards, and the standards are made to be respected. If you don't respect them, you don't know what you're going to do. And of course, whatever is generating the request is going to initiate the thing, and the response creator is going to say how you should cache it, okay? Usually you interrogate a system, and the system knows way better than you what is going to be cached, how it's going to be cached, okay? And you can send additional information to help return the best response, and then you exchange those specific HTTP headers both ways. That's the principle, okay? And what would the best practices be like when it comes to HTTP caching? Well, first of all, you have to remain RESTful. One method, one address, one action, one response. Which means, basically, if you take a URL, a complete URI with like an anchor, you see what your screen is doing, you take it, you make a screenshot, you have someone with the same computer as you do, exactly the same computer. You copy and paste this through instant messengery, MMS, email, Discord, whatever you want it to be. You put this to people, they click on the link, they open it, they should see the same thing that you see. Maybe they should be connected for some reason, but if the URL is public, you should see the same thing, the same action, same results, okay? So that is RESTful, and also it shouldn't be variating according to the context. So you add the HTTP cache headers to all your responses. I mean, at least you should check that you are not caching. So that would be the strict minimum. And then you just, when DAP says, well, you're going to have to cache for a long time, this is 1 year, you say, all right, we're going to cache for 1 year, I don't care. And then remember also, one good practice is not to use post, HTTP post, which is the second most used after get, when you don't need to post data. Post is frequently used instead of put, patch, and delete, mostly because of HTML support for formulas, okay? So, but the thing is, you should not use post instead of any other methods when it doesn't need to, okay? Especially for API, you see? So, you know about, how to say so, this is the same as when you go to a restaurant when you don't want to look at the prices on the menu because it's super expensive. You got that infinite cutlery. You got so many forks, spoons, knives, glasses, you don't, wow, and plates, you're like, this is, how am I going to eat? There's so many of them, you know? You know those restaurants when you book a table, whatever the time, your appointed banker calls you straight away and tells you to get out right now, you know, those special restaurants when you think about. You end up with 5 forks, 4 spoons, and cutlery you cannot name because it looks like dentist stuff. You're like, what am I supposed to do with that? So in the end, you're finishing your super classy soup soup with a knife, you are cutting your meatloaf and vegetables with a straw, and using water glass to ask for more wine. That last one might be actually done on purpose, maybe. But yeah, this is HTTP post. HTTP post is when you end up in that super classy restaurant eating with your fingers. It works, but everyone who knows how to eat there is looking at you, frowning, and you'll mostly end up fired outside, okay? So don't do this in a super classy restaurant. And also, a few more tips. First of all, don't reuse and response-specific content when you don't need to, because you got server-side includes or edge-side includes, like we saw that. So you can optimize this. You don't need to resend everything all the time, because maybe it's going to be savvy if you just send all the response that can be cached and a little one, just like we saw in the ESI. It's just the same principle. Also, you should add content length to all your responses. This is very technical advanced things, because if you do so, your responses can allow persistent connections. If you have a connection that's open and into the payload, you find the word done, D-O-N-E, it's considered as being the end of the persistent connection. So if it does that, it closes the connection and creates a bug, actually. So if you just get content length to all your responses, the receiving device knows what the payload size is about. Okay, so that's just pretty complicated. So you start with larger files. So like I said, it's just going to save your network, your bandwidth first. And then you have small tricks. Like if you have assets, like images, you can add an HTTP GET parameters to assets that you need to force update expiration from caches every time you update your website. Drupal does it by default. Symfony has an option for that, for example, too. So you can split the responsibilities between your backend applications and your web servers. Okay, so you can just know which one of them is going to generate which part of the response. Okay. So could be your app sending the headers, or could be the server saying, I'm going to handle for the images and CSS. You don't need to go through your backend in Java, PHP, whatever it's going to be. You don't need to go for that, okay? It's just a file that is sent. On Apache, you got that -f function, If it's not a file, -d. If it's not a directory, just return the response. If it exists, but if it is a directory, just open the directory if you have the special mode to list what's inside. If it's a file, just return the file. It's never going to your backend. So you have to split the configuration between your backend application and your web servers. Those we saw in the previous slides. Okay. All right. Now, how does this work? What's under the hood? When it comes to HTTP way of caching, put some air quotes, and not how you should cache. It's not the same thing. There are two concepts, expiration and validation. Okay, so expiration is, hey, bro, I got the stuff here. Is it young enough? Can I just reuse it, or is it just rotten? And validation is, this is exactly what I have. Should it be the same thing that you're going to return to me if I just ask you one more time? Okay, this is the difference between expiration and validation. You compare things with validation, and you just check that they are not stale when you expire, okay? So expiration is just better for the resource that just never change, that are more stable, and when things become dynamic or less predictable, like it's going to be random, it's going to work or not, it's going to have results or not, you should use validation. And the thing is, expiration is super easier to set up than validation, because expiration just goes between your browser cache and your browser cache itself. It doesn't need anything else. Validation needs the whole round trip to the server, but your server is going to determine if it's going to be bad or not. So you have to compute validation on your backend. Validation is about saying, all right, I want this pizza here, and I want for example, if I'm not going to take the pizza example. If you have a credit card number, that's really super sensitive, okay? You say, okay, do you have the CVC code for this credit card, which is not really good to store. Like, actually never store this, okay, but let's suppose we can do. And the person is going to say, yes, or do you have, for example, my last name and first name for my ID card number, okay? Then you're going to have to go for a super huge database. And it's going to take a long time, okay? So, yes, you are William Pinault. I know your name, okay? And you get the response and you say, okay, I'm going to mash the response and make it into a hash, a number. So I'm going to ask you, do you know what's behind this ID card? And the last time it was asked, you send me this hash. So you have a special cache, for example, on the server side that is faster than database querying, like we saw earlier, and you say, I'm going to check the cache. And the cache says, yep, I got this, and it's considered not stale, so it's going to be the same. So you don't give up the response. You just say, it is going to be the same. You don't get the value. You just say, it's the same, okay? That's the difference between expiration and validation. Validation would normally save network usage more than CPU usage, actually, because you have to do something on the backend side. That's the difference, okay? So, for example, expiration mostly uses those two headers, expires and cache control, okay? So that's basically client server. You just send a time and you say, hey, I got this time and it's going to expire. You can keep it in the caches and in the shared caches too for a certain amount of time. So this is what it says. You know, the server says, by the way, your thing is going to expire into some further ahead part later on. Okay, so you just return information in response so that the caches know what to do the next time. The problem is that the time is supposed to be a universal one, which is on the internet not really universal. And validation mostly uses those two headers, etag if not matched, which use they are the server side and the client side one, and last modify and if modify since or if not modify since on the client side. Okay. So the matching response headers that go along response one, you should just return another piece of information in response, and the next time the browser, the source, basically said, hey bro, what should I do? This is what I have. And the server guesses it has to compute a new resource, a new response, or simply answer, what's up bro, you know what? You're still fresh bro, you're good. Here's what it simply was about. And you return an empty response, but with context. Okay? By the way, etag means entity tag, so it's associated with the entity you are requesting, okay? And on top of those things, like I said 2 slides ago, that's also how you should cache part. This header has a lot of options, so here are the most common ones, the cache control headers. And this is really tricky, actually. You can say how the response should be handled by the cache. Once it determines that the cache could be cacheable, the response could be cacheable or not. If it's public, you can store this into all the caches, browser and shared caches. You remember the N one, the one that generated the request, and the intermediary ones, okay, the shared caches. The private keyword means you can only store this into the browser cache. The proxy, for example, forward and reverse proxy, should never store this. The max age, the maximum age, works pretty much the same. It says you can store this long in the browser and in shared caches. And you've got the S for shared maximum age. You can store this long in shared caches only. Then you got the most tricky one, the one that everyone gets mistaken about. No cache doesn't mean that you're not going to cache. It means you're going to cache it, but you can check for the remote every time. And no store means you simply shouldn't even put it into a cache. And then you got the last two ones that are interesting to me. The must revalidate mean please use freshness headers all the time in browsers and shared caches, okay, the ones we just talked about this one. And proxy revalidate means please use freshness headers all the time only in shared caches, okay? So there are 10 more options or 12 more options, I think, into these cache control headers. It's quite complex, but okay. So as before, let's illustrate how this works. So first, this is the way things normally happen the first time. You just send a request, you miss the cache, the request gets forwarded, and I mean, anywhere here could be your browser cache, could be a forward proxy and a reverse proxy, all of them, okay? They all work the same way, follow the same things. Then you get an HTTP headers response, and you've got here the expiration and validation headers, you know, those you're gonna use as a response. You basically get an HTTP 200 code, which is okay, which means it's a default behavior. This means your page was checked and it's working fine. Here is the response. okay? And then you've got, once you store it into the intermediary cache, once again, your browser, a reverse proxy, forward proxy, whatever gateway you want it to be, you just send back this response unaltered. It's just the same, okay? It's just forwarded the same way, because it's very important that the response doesn't get altered this way. Then if you use expiration, you just do the same thing, but this time you hit the cache. So you never leave the cache, you just read it, and you return the exact same response with the same headers and the same body. And actually it's going to say, by the way, the age of the cache here is n seconds and whatever you want it to be, okay? And probably an age header. You don't have to provide it, but it's better if you get it, okay? And the validation is really different. As you can see, it's a little more complex. You go to the backend server, you bypass the cache, you give and you provide as a client here in your request everything that is needed. By example, for example, you just leave this is your browser, and your browser generates this. So you say, hey bro, I got this. Has it changed? And of course, the generating device will not add those headers if it lost the response content. Otherwise, it's just pretty nasty. So your application server determines if it needs to go all the way through the response calculation or not. And if not, it should return an HTTP 304 not modify response header only. That's right. Bingo, you don't have the body. You didn't need to generate the body. You're just saying, you remember what you did last time? Well, you say that you had it in cache. Use the cache as the same thing, okay? So then the cache system should handle this and complete the response body with what's been previously stored. And that's it. That's the basics of HTTP validation. By the way, you can have a 200 by the end. It doesn't have to be a 304. Like, this has to contain the body. So you take the body response body in the cache, which is really way faster. And actually, this doesn't even leave your network. If this is a browser, this is inside the same process. You don't even leave anything else, okay? That's it. That's HTTP validation basics. But yeah, some people want to watch the world burn. Or maybe not. Because actually, mixing both concepts ends up being pretty good and fine-tuned. So you can use it, but how does it work? It's especially simple. They obey a precedence. Expiration goes first all the time, and then if expiration fails, like it doesn't work, it uses validation. Okay, so if expiration is stale, like it's too old, then validation checks that maybe it's too old, but it still didn't change. Okay, so a response will expire first, then fail to validate, and then it will be regenerated. Okay. And we almost finished. Then don't worry, just press your nose so that the nose bleeding stops, because I know you guys are tired of this presentation, but yeah. One last shot. Let's talk about the JavaScript cache in browsers. As you know, all modern browsers now entirely rely on document object models, which is a standard specification to read, manipulate structured contents, and styling of HTML and XML and HTML documents. But in addition to this, modern JavaScript is getting more and more used for other purposes, such as accessing cameras, microphones, gyroscopes, magnetometers, sensors, etc. That ends up being a whole pile of whatever you want to call this. What does Ian Malcolm say in Jurassic Park next to the Triceratops already? Anyway, we'll talk about service workers in a minute anyway. So yeah, general considerations: you shouldn't change your code for no reason. You should the front-end code, okay, the JavaScript, and you shouldn't recompile, redeploy for small secondary reasons. Just try to pack up your deployments, even though the CD promise is a hell of a thing. You need to separate unlikely to change code from likely to change code, okay? Most of the time, libraries and custom. You have to watch out how often your libraries will change, especially with NPM, where it changes every day. This might help. Also, you shouldn't change URIs, so the complete universal resource identifier, the FQDNs, the fully qualified domain names, the paths, the get parameters, the hashes, nothing should change. So try to be try to remain similar in your URIs. Be careful when using chunks, like if you're using Webpack Split Chunk plugin. You got the Webpack Analyze tool if you want to make sure your chunks didn't move, because if you have lots of JavaScript that is too large for a browser, then gets chunked into pieces by Webpack, and you got like 30 kilobytes of JavaScript, and then the next 30 kilobytes. If you change something that's got the beginning of this chunk, it's going to move and shift everything back, so all your chunks are going to be renewed. So the browsers are going to download one more time all the chunks, okay? And for example, Chrome doesn't cache anything that's below 1 kilobyte of file. So you have to group JavaScript because it has to reach this threshold of 1 kilobyte, okay? And remember, some part of caches only work in browser tab, which is the worker of the thread context, like the prefetch cache that I'm going to talk about in a second, okay? And then, if you don't know what to do and you don't know how to handle the browser cache, you can use service workers. What are those? We're going to talk about that in a minute. And first, before we talk about this, service workers, we have to think and talk about some ways you can actually, hit the cache. So like I said, you're going to hit those browsers, but they have generic specifications. I found most of these things in V8 blogs, actually. For example, when calling the same function, if the parameters type differ, the system will try to re-optimize the function. But if you use the different types for a call, it's going to change. So this is called megamorphism. So you should fix functions, argument types at call. I'm going to explain that first. If you just call a function with anything as a variable, and then you provide an array and an object, then an object and an int, then an integer and a float or a string, then a string and another string, every time you do this, the whole JavaScript engine is going to recompile and re-optimize the function, and it's going to bypass the cache. So this is called megamorphism, okay? So for example, Chrome just stops after 4. When it just finds 4 calls for the same function, it says, all right, you don't know what you're doing, I'm going to stop this, okay? So you should avoid random things, like math.random is the perfect example, but there are many other things. So if you just don't need randomness, don't use randomness. You should declare properties in constructor functions. Now is part of the, not the latest, but close to the latest ECM script things, You should fix function argument types at call, okay? The object ordering is important. If you got A1, B2, C3, it's going to be different than if you got B2, A1, C3. So it's not going to be the same thing. And the immediately invoked function expressions will force intermediate caches. So if you just have this, when you declare this, the JavaScript engine say, oh, there's a parenthesis here and one here and this call. It means whatever is inside has to be called just after being passed. So this is going to force the components to be cached first. So it's going to be faster. If it's read first and put into cache, then all the subsequent calls to your thing here are going to be faster. So this is a way to slightly trick out your things. Also, don't declare classes below script scope, which means you shouldn't declare classes inside functions. For example, you should only instantiate them if you need them, but don't declare structures in general outside the global scope. Okay, don't do this. Just has a class keyword, whatever you want it to be, at the root of your files. Okay, and please note this applies to the backend JS code as well. Okay, and some of this advice here could be taken from other languages too. Also, the for in loop, the for something in loop is by far the fastest way to do the iteration, to iterate over something. Okay, so the for in loop is super high. And one last thing I wanted to talk about, which is really important, and then this talk is over, I swear. The new shiny thing everyone is looking at now, service workers. Those are the consequence of a few things. First, everyone now uses a smartphone more than a fixed position landline connected device. Second, the bandwidth of GSM network underlying the 1, 2, 3, 4, 5, 6G networks are limited by distance, topology, population, and random stuff you don't want to dive in right now, like hello beamforming. And 3, most mobile usage is actually using a private connection, local devices, namely Wi-Fi devices. Otherwise, people are very often without a network, with a stuttering network that doesn't work, or within an insufficient network one, you know, just like you expect 4G or 5G, it's just going to be really lower generation network, okay? So here's what they are at a glance. By the way, please note I had a whole talk on PWAs and service workers from 2019. It's still valid, though many things improved and would really need a little refreshing, but also it's in French, I think, so I didn't have a record on this in English, but if you're French, you should just take it out. So what are service workers? It's a W3C specification, mostly pushed by Google. It started in 2014, it's been settled down in 2019. It's part of the progressive web application paradigm, which is a way to it's just a whole talk. It took me an hour to explain what they are, but basically the native applications are being deceptive and the web is being cool, so we need something to take the best of both worlds, okay? So those have safe and open specification. It started in 2018 for Google Chrome, Safari, then Firefox, then Edge, and basically there are a JS worker component that offers lots of things like rich offline experiences, background synchronizations, push notifications on web, yeah, just like you got on native Android or iOS operating systems. You can provide analytics, you can provide front-end failover, client-side load balancing, lots of things you could do with that. It is imperative to note that those are components that do not access the document object models. They do not access the IndexedDB, the local storage. Like I said, those are different components. They do not access this, but the DOM can access this. So your JavaScript into the DOM can access to service workers. So if you want to use them, you should use specific HTTP headers. You don't have to, but it's better if you do this. So on request, you say, hey, I want to use this. And the server should allow service workers allowed to say, is this allowed or not? To say if maybe you don't want to use them, and maybe they don't work well with servers. So if I wanted to summarize the cache part of service workers, just like I did for the previous concept, this could be a way to represent what they do. This is not how they work, this is how you could ask them to work. They are not automatic, you have to build what you want them to do, okay? So let's suppose you're generating user agent, what we call a user agent. Is generating an HTTP request, it's possibly using a service worker, and it's going through the internet here. So you just say it's going out of your browser. Then this request could be hitting a service worker, okay? But then you're going to say, I could get the response from the outside, but I could also ask this service worker to handle this for me and to make like an intermediary management that says, maybe you should not go to the internet, and maybe if you cannot, maybe I have the response here with me, okay? So that is what your browser is going to do. So if you got this, you just got the response and you take it from your cache. But the difference is it's not an automatic process here. The service worker can handle your browser cache manually or as you want it to behave, which is really, really different. And what's the code? What's the code? So this is the code. That's one way to do the stuff. So let's look at it. So part one, we just see how we can tell a browser that we have done, and we have one service worker, and we'll see what it can do. So if the navigator supports service worker, then we just register this. What is a service worker? It's just a JavaScript file, whatever you want it to be, okay? And then, or this is a URL actually, so you can put whatever you want it to be as long as it's JavaScript behind it. So you say it's a promise, then you register it, then if it fails, boom, the worker failed. So it's going to be cool, yes or not. And then you give it a scope. The scope is whatever sub-part of the URL of your application the service worker can access and see. It's just like those things you put on horses, to prevent them from looking on the side. The service workers is contained into this scope. It cannot go further. It cannot go below. It can only go deeper into your URL structure. Okay, so if you got /1/2/3 after your HTTP domain, for example, if you say the scope is /2, it cannot go to /1, but it can go to /2/2/3, for example, or /2/4, whatever you want it to be. Okay, then you just install it. You have a function that say whenever it gets installed, this can trigger, and then whenever you activate the service worker, you can do this too. Okay, so then you have different way to use it. You all done and you're ready to work with your service workers. Okay, so you can have a service worker when you're just limiting what they are doing to the cache, which is the purpose of this talk. You can say the service worker can only fetch the cache. Yes, you can do this. You can do this for a page that can only go to the cache. This is not a very good idea, but you can do this, okay? You can go only to the network, which is you never use the cache, whatever the headers are, whatever you're going to be. And then you can have the cache and then fall back to the network. This is just brilliant. If you have a network falling back to the cache or cache falling to a network, it means you are going to aggressively say that you should use the cache first, and sometimes for some reason you can then fall back to the network. This is just a rich person problem. The poor person problem is that you don't have a network next to you. Like I said, sometimes it's falling down. You don't have the 4G, you don't have 3G, you don't have an external network. The bandwidth just go down, it's just saturated. So what would you do? You say, I'm going to try the network. Is it failing? Yes, just pick up the cache. And if you do this, you can have an application that responds pretty fast, but at least it doesn't crash, it doesn't display a bug, you don't have this white page on the browser, it's still working, it gives the feeling of working, you know? Or you can also say you want to use the cache, then you're going to use the network, both of them, okay? And then part 2, you can tell whatever code you want to be run. So basically regarding cache, service workers, again, they do much more than this, but this has been their most popular use so far. You can just add or remove item from the cache. So here we just wait with an event listener for browser to browser events. We just wait and listen to browser event, like fetching resources, which is what JavaScript calls when it just goes to an outside world request. You just here, for example, this first example here just puts a pile of items into the cache. So you get the cache and you say whatever you want it to be, don't create a pool, just a cache name. You open the cache, whatever you want it to be, name it my cache, whatever, and you just put these items into the cache. So once this is done, your browser has this and it's going to use the cache. First of all things, okay? So when it needs to use the cache, it will just interrogate your service worker first with the fetch event, okay? So first, when you install it, you just preemptively add this. This is really static and stupid, but you can do this, it works. And then we can define a custom pool cache for that. And then we can also alter how the browser is going to fetch the event. So if we got this, you can have the event and we can fork the response to the cache here. And later on, we go cache first, falling back to the network. So if you do this, for example, you can have this, you open your cache in the first example here, and then if it works, and if you just open the cache and eventually just gets done because it's a promise, you just find if you got something in your cache that is working. Otherwise, you fetch the response, then you just return the response and you put it into the cache and you return it, okay? So that is the same thing we called memoization in the large scale, and that's the first pattern we used on the first slides of this presentation. And then if you just listen to the remote sources, you can go cache first, and then you can find whatever comes in first. This is just the pretty most standard use you'll do with service workers. And also, a few last things before we just leave. Having mentioned HTTP as a cache protocol, what about HTML as a cache language? I mean, we talked about ESIs, but just for standard browser to server cache, there is still, but there was actually an HTML5 component. It's what it used to be is dying now. For a good reason, it got replaced by the service workers we just saw. So if you're just curious about it, it's just dropped in Firefox this year. is going to be dropped after a lot of patches in Chromium. In Chrome, it's going to be dropped in the next coming versions, slowly and slowly. It's deprecated in Safari. So yeah, so the cache API, which is what we just talked about for the service workers, is working. So you could have this manifest cache, app cache, and you had to set up things, but this is gone. Okay, this is gone, long time, let's see, and service workers are going to replace it. And finally, about browser caches, because that's the last part I wanted to talk about browser caches. I won't go that far into resource caching, how the browsers maintains images caches and how they optimize those. This is really not worth detailing, but you have to know that the preload cache is straightforward, the image cache is straightforward. Remember, the preload cache is only working into the same tab most of the time. Your browsers get indicated what to do in the context of the current page, so that's network bandwidth and CPU to be saved. But if you want to be saved, you can prepare a linked HTTP request. If you want to fluidify your network experience with preloading and preparing, prefetching, okay? This is suggested by the appropriate HTTP headers and the HTML tags, okay? One more thing about I didn't talk about, the server push cache. It still works, but the server push is actually making things more complex. And surprise, the browsers are dropping this one by one. Chrome is the first to do this. Because actually it was not really widely adopted. It was more a problem was the solution, so it's being slowly pushed away. So yeah, let's not talk about this for too long. And last but not the least, make sure you master caching before you use the vary header, because it's supposed to sustain polymorphic responses for a similar request with different forms of the same answers. And in the end, browser mostly uses as a validation header. Basically it's just an e tag that is going to be altering this vary. It's not good, so you should just avoid using this server, okay? And let's conclude this super long yet super deep talk. This is not the end for you. If you want to go further, you can try to go deeper in those topics. I didn't talk about testing, for example. Lots of things I didn't talk about. I didn't talk about testing in cache because it's really interesting topics as much as delivery in cache. For example, we just didn't talk about this. I didn't talk about virtualization caches, but if you use VMs or containers, if you build Docker images or Kubernetes networks of nodes for your internet system, information system, you probably know what I mean, right? You know that Docker uses caches and everything does. So I didn't talk about DNS caches, even though they are web cachings, but there's not a lot to say about these, browsers and DNS servers, mostly for internet service providers, managed service providers. They use a hierarchy of servers for domain resolution, and spoiler, this can be attacked too. It's called usually like DNS poisoning, but it's not anything. This could be a slide one day, but not much to say about this. And also the network caching, I didn't talk about this because it's pretty straightforward. Just like I talk about CPU and low-level caches, I could talk about low-level network caches like roots caching. You all, I think, notice that if you're doing the same thing twice on the internet, even if you refresh the cache and empty the caches, it's going to take less and less time if you do it over and over, because if you do something very often, then the network wizardry is going to stabilize what you're doing, and it's going to say, oh, this guy is asking the same thing over and over to the same server, so let's establish a secure and permanent routes. Let's not go to dynamic calculations of nodes and networks, okay, and pathing, okay? So this is interesting too. And how we manage to optimize worldwide bandwidth, magic wands and Tony Stark working on wires all day. But I think this goes outside the purpose of this talk as well. Could be debated. I also didn't talk about the maths, the checksums, the hashtags, the hashes, the cryptography, the fingerprints, the cryptographic hash functions, etc. Though I mentioned a lot of things that belong to that fundamental research domain, I chose to let this out of this talk too. And finally, I also didn't talk about load balancing, because even though it goes the same direction as caching does, which is performance, reducing loads, making systems work better, it's still really outside of this context of the context of this presentation. Because, like I said, load balancing by itself is a whole talk at network level, OC model levels, internal applications level, services, microservices, round robin, queuing, network modelization, etc. So yeah, I chose not to talk about this because even though this is really interesting, it falls down on discussing and explaining whole optimization mechanics that are not caching. And again, you just find those very recurring applications to do load balancing. So before I leave you here, remember that everything I described in this talk can be load balanced due to high load. Everything we said, statically, dynamically, can be load balanced, okay? So if you are just super interested, there were a few config examples from free solutions, NginX, proxy, and Traffic. There are many, many more of them, as you could expect. You define front-end and back-end streams, locations, addressing, what protocol you use. Most commands are HTTP or TCP in our case. That's what I won't go too far into load balancing, because this will be a whole entire new talk and leaps outside the cache considerations. Okay, so you see we just got the same configuration over and over, and this is still super basic configuration. You can have really more advanced things than this. So I won't go too far into this, because as Michael Ende once wrote, that is another story and shall be told another time. So this is the end, beautiful friend, this is the end. Now it's turn to test if you didn't know about these things before. Don't forget that if you want to test results, you should use CPU, memory, HDD bench. There are many tools out there to benchmark your whole system, like Siege. You can use APMs, application performing monitors like Dynatrace, Datadog, Sentry, Neuralink, or providing tools to take a look at that, just like Blackfire, if you're using PHP, for instance. It's a pretty good tool. But the purpose of this talk is not about testing your cache system and the global performance. It's how you should do such a thing. You should do such a thing, but you should just do the cache implementation. You should not review with me right now how you're going to test it, how it's going to be more or less efficient, okay? Because maybe, I say maybe, there's a chance you didn't pick up configure or chain tools correctly. Observation is always the start of the thought process. And that's it. I think we've been through major consideration. One last thing though, be careful not to over-engineer your system. You might actually end up consuming more energy, trigger time to first byte increase, delay wall time of request and response, misconfigure solutions. Also, this is costly, so the time needs to be fixed with your customer if they don't have the time to invest into that. You might end up creating chimera systems that are very hard to debug and maintain. You may end up adding complexity to any working system. You could also this could make you be chased by your IT colleagues with an axe through your working offices, which is not nice, except if you are Gimli. So don't be fools when trying to optimize your architectures, because unfortunately caching is not the solution to everything. And I just put this adorable Douglas Adams quote on the end because I wanted to end up like this. So yeah, I hope that this little talk will provide you with ideas to you, that you'll be eager to dive further into those concepts. I hope that you will face architecture optimizations and web technology chains and stacks with more confidence next time. And lastly, I hope you'll be able to better know your information systems and design better ones. In the end, let's all save energy and with that, our planet step by step. Because after all, we're also responsible for that, and as you know, we're facing a hell of a challenge nowadays. We still have backup servers, but we don't have a backup planet. As usual, you can reach out to me on every link and social network I gave you at the start of this presentation. I'll be more than happy to discuss with you. Should you have questions, should you make mistakes, or should you want to discuss about anything. Thank you again for staying until the end. I hope this was clear to you and hope you learned something. Thank you very much. Cut.